And we're back. So on today's show, what a circumcircle is and what an incircle is. So just so we're clear, you give me any generic triangle, triangle ABC. There exists a circle that passes through, in theory, all three vertices. That's right, that circle's just a little fat over here, that's all. Just a little bit thick. Okay, well, in theory, there is a circle. I missed it again! That passes through all three vertices. That is called the circumcircle. There is also an incircle, a circle that is tangent to each side of the triangle. We will look at both of those. It turns out that the circumcircle is centered at the point of intersection of the perpendicular bisectors of the sides of the triangle. And this is a result that you may remember from high school geometry. I know currently in New York State in high school geometry, this is taught. So I have a triangle. Triangle ABC. And I want to show that this point of intersection is the center of a circumcircle. And here's the basic argument. If I were to draw the perpendicular bisector of BC, any point on that red line is equidistant from B and C. Any point on that red line. Similarly, if I were to draw the perpendicular bisector of AC, any point on that red dotted line is just as far from A as it is from C. So here's the thing. In Euclidean geometry, these two segments have to cross. They must cross. In neutral geometry, either the lines are parallel or they cross. Let's assume they cross, just for the time being. Let's assume those lines cross. If they cross at some special point O, then that point O is on this line here. And so OB is congruent to OC. But that point O is also on this dotted line, so OC is the same as OA. So now I have OB and OC and OA, and they're all congruent. So they're all congruent to each other. And so these are radii for the circumcircle centered at O of radius R. If the perpendicular bisectors intersect, then the triangle can be circumscribed for that reason. If the perpendicular bisectors intersect. If the perpendicular bisectors do not intersect, then there is no center for your circumcircle, so the triangle cannot be circumscribed. That is a big deal. That is a big deal. I will in fact prove, the other thing that I prove when we show up in class is that if the Euclidean parallel postulate fails, if we're in hyperbolic geometry, then there exists a triangle that cannot be circumscribed. Cannot. And we actually build it. We actually say, pick your favorite Sakari quadrilateral, just your favorite one. We know in hyperbolic geometry, well, we know in neutral geometry that we can take a midpoint here and a midpoint here and drop a perpendicular. That is the mutual perpendicular for lines AD and BC. That is the one mutual perpendicular for those two divergent parallels. So we know by properties of Lambert quadrilaterals that MN is shorter than DC or AB. So we just extend this just a little bit to some point E. Well then, here's a Sacchari quadrilateral, here's a Sacchari quadrilateral, and when I do this, I have, well, I suppose we'll put the rest of that together when we gather in class. I argue that that picture shows that there exists a triangle that cannot be circumscribed. Cannot. Okay, so the other thing for us to look at is an inscribed circle. Now here's what we argue for the inscribed circle. Take some generic triangle ABC. I argue that the incircle is centered, oh, back to slide 1. The incircle is centered at the point of intersection of the angle bisectors of the angles of the triangle. You draw the 3 angle bisectors, they come together at a special place, and that special place is the center of the incircle, the circle that is inscribed in the triangle. This is what you will prove when we gather, but I'd like to give you a jump start if I can. I think we can draw an angle bisector from B to some point D. Those are congruent. Now we have triangle DBC. We bisect angle C. We bisect angle C. Crossbar theorem says that these have to cross. Maybe we call that point of intersection I for what will be in center. You have to show that that point is 2 things. You have to show that that point is on this angle bisector. We don't know that yet. And you have to show that this point is just as far from here as it is from here as it is from here. That's what it means to be the center of the inscribed circle. That point is equidistant from the 3 sides of the triangle. Now, with that drawn in there, you got a whole bunch of small triangles that are congruent to each other. I'll let you give some names and finish the job. Any 3-letter word will do for that. I'll let you finish that job when we gather in class. That's one of the things that you will have to prove. Hey, speaking of inscribing, you can inscribe just about anything in about anything. So you can inscribe a circle in a triangle. You could inscribe a triangle in a circle. You could, given a circle, pick a point and say, okay, I'll head over this far and I'll head over this far and I will inscribe an equilateral triangle. In theory, that's equilateral, an equilateral triangle in the circle. Or you could take a square and say, okay, I'm going to come over here and draw this, and I'm going to come over here and draw this, and I'm going to come over here and draw this, and that's a square. So your job, your other job when we get to class, question 5 in our lesson, will be to ask you to show that it doesn't matter if the polygon has 3 sides or 4 sides or n sides, I can inscribe a regular polygon of any number of sides in a circle. That is a fairly straightforward thing to prove. I will let you prove that when we gather. Okay, that's enough for now. Next up, Euclidean geometry.